We demanded of the entropy that if we plotted entropy as a function of the internal energy U, this function was an increasing function of U. It was a monotonically increasing function of U. It was a smooth continuous function. Okay, it was the second requirement. It had no discontinuity and its derivative existed at every point. From here, we said the slope delta S by delta U as a function of V and N, with V and N kept constant, was just 1 over the temperature. Then we spent some time the last time trying to describe why this was a sensible definition of the temperature in terms of taking a large system broken up into two subunits, 1 and 2, first preventing energy interchange between these and then allowing energy to go from one to the other, and then asking what defined the equilibrium in the sense of the maximization of the entropy S, which was the same as maximizing over some division of energy U and U total minus U between S1 plus S2, where S1 and S2 are the two parts of the system. And then we said that these two parts of the system were in equilibrium when the temperature here was equal to the temperature here. Then we said that given S as a function of U, V and N, with these properties, that X was extensive, it was a smooth function, monotonically increasing, and for every U there was a unique S, we could go from S of U, V and N to inverting this relationship and writing U as a function of S, V and N. Having done that, we could define du to be T ds minus P dV plus mu dN, where these quantities T was defined as delta U by delta S at fixed V and N. The minus of the pressure was defined as delta U by delta V at fixed S and N, and the chemical potential mu was delta U by delta N at fixed S and V. These were all our definitions. Then we said we could think of this in another way. We could think of this as the heat transferred to the system, this as the mechanical work done on the system, and this as the chemical work done on the system. So if you wanted to change the energy of whatever system that you were trying to study, you could do it in the following ways. You could add heat to it, you could do mechanical work on it, or you could do chemical work on it by changing the different numbers, the ratios of the numbers of moles present in that particular system. Okay. What we didn't do, and which we could do, and maybe you could do it for homework as well, is to apply the maximization of the entropy idea to the case where the wall between the two subsystems 1 and 2 was a movable wall. Once you allow the wall to move, now you can ask, where does the wall position itself? What determines where that wall is? So that is some division of the volume V between system 1 and V2 of system 2, with V1 plus V2 equal to the total volume V. How exactly the volume is divided between these two subsystems is determined by the equality of the pressure here. The pressure here must equal the pressure here. Similarly, if we put a wall here and then allowed particles to move across this wall, then equilibrium would happen when the chemical potential here was the chemical potential here. So all of these conditions on equilibrium is, first of all, if you want equilibrium against the transfer of energy from one part of the system to the other, then the temperatures have to be the same on both sides. If you want equilibrium with respect to some change of volume between the two sides, you want the pressures to be equal on both sides. If you want equilibrium with respect to particle number interchange between one, you need the chemical potential to be the same. So all of this makes a lot of sense in physical terms. You know that any wall here which can move can only be balanced when the forces on it are the same from both sides, which means the pressures are equalized on both sides. So we have got this far really by postulating the existence of a function S, which is the entropy, with certain properties. So now the question would be, what is the interpretation of this entropy? and especially from a microscopic point of view. By microscopic, I mean in terms of all of the little atomic degrees of freedom that we have ignored in just saying that it depends upon this, this, and this. So this is a question that we would like to understand. What is the entropy? What does it actually mean from a microscopic point of view, and how do we understand it? Okay, so let's just do one more thing here before we go on to doing something completely different, and that is to say that the condition that you maximize the entropy. So suppose I fix the energy U, and I have a bunch of other parameters here, which are all of which are extensive. That we call them x1, x2, x3. And here, for example, this might be the volume, this might be the number of particles, but I could have other extensive parameters that determine the behavior of my system. Suppose I now allow any of these to vary, I must still maintain the condition that my entropy must be maximum. So this says that I must maximize S at fixed U. I must choose a configuration of x1, x2, x3, provided I can change them, such that my entropy is maximized. Now this is a condition on S, but I can also look at this as a condition on U. So I must minimize U as a function of S, x1, blah, 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 right up to any number xn, where all of these are the correct extensive variables. Okay? Now, this is something that we postulated in the beginning. This is something new. But these are actually the same thing. Maximizing S at fixed U with respect to changing any of these other parameters is the same as minimizing U at fixed S with respect to these other parameters. The simplest way of explaining this is through a physical argument. And that is to say, let us assume that having fixed your S, you are not at the minimum of that U. Let us assume by contradiction that the system prefers a state or chooses a state which at given S does not minimize U. Okay? So now what this is saying is, at that S, I can now extract energy from the system until I push it down to the minimum. Because it's not at having fixed S, I can make the system do work that doesn't change S, but changes some of these other coordinates, and from there I can extract that energy. Any energy that the system, any work that the system does reduces the energy of the system. So now I come to a new energy. That energy that I have extracted from the system, I can now give back to the system in the form of heat. Okay? Any work that the system does which helps it reduce its energy is now given out to the environment, to the surroundings, to something, to some additional subsystem that I have there. I can now convert that work into heat. I can always convert work into heat. It's just as though just friction is an example of rubbing two surfaces together and generating heat from that. So the work I do in rubbing the surfaces together is completely transformed into the heat at the contact point. Having passed that heat back to the system, I increase the entropy, because I know that adding heat to the system dq increases the energy, increases the entropy of the system. Okay? But now I have a system which now has a larger entropy than the system I started out with, even though it has now the same energy. I just took energy out and I put it back in. I took it out in the form of work and I put it back in the form of heat. So now the energy is back to where it started, but now the entropy is larger. So that is by contradiction. That contradicts this statement that the system always likes to choose the maximum S for a given U. Therefore, it must also, this condition must also imply this condition, that the system likes to find the minimum energy if with respect to varying any of these parameters once I fix the entropy S. Okay? So this thought experiment can be made more formal and more useful, but at this point we don't need to do that, because we don't want to get into the gory details of understanding thermodynamics. We just want to understand as much of it as we need to and come back to these points later. What you need to remember from this discussion is that you can change the energy of the system in multiple. The energy is a state variable. It describes the state of the system, and it's uniquely associated with the system in equilibrium. You can change this energy in multiple ways. You can change it by doing work. A state variable is a variable that describes the state of a given system completely, the thermodynamic state of a system. If I do not tell you what this variable is, you would not be able to know what the state of the system is. So given a particular system, Let us say the system is completely enclosed. It cannot change heat, exchange heat with the environment, exchange energy with the environment, do work, etc. Then it's a fixed U specifies that system. If I do work, I can go from this U to another U prime if I do work or add heat. This is a statement to the conservation of energy. It says that the change in energy of the system comes because I transfer heat to the system, I do work on the system, or I add particles to the system. That's what the different components of the change of energy. But I always have a way of assigning the energy that I put into the system and finally leading to a change in the energy U. Okay? The new thing about thermodynamics is this part here. It recognizes that there is a way of transferring energy. Heat is a way of energy transfer. So this line here, this part of this line recognizes that there is a way of transferring energy to the system that does not rely on changing any other macroscopic parameter inside the system. It just relies on changing some secret hidden behavior of the system as encoded in this function S. And if I transfer heat to the system, I increase S. And all of thermodynamics is essentially concerned with transferring heat to the system, removing it, and asking what are the consequences of it. As it turns out, you can add heat to the system in the form of by increasing its entropy. But if you want to convert all of that back to your initial state, if you want to take all of that heat and convert it to work, then you cannot do that in a 100% efficient way. There are important constraints that govern the transfer of energy to the system in the form of heat. Not all of that heat can be extracted when you go back. There are also constraints that have to do with the fact that thermodynamic processes on large systems are unidirectional. They move in the direction in which their entropy goes up spontaneously. They spontaneously do not go to a system in which the entropy goes down, which is why your coffee cup always cools, because that corresponds to the system in which the universe has a larger entropy than your initial state. Whereas the state in which your coffee cup would spontaneously heat up would be a very, very low entropy state. So the chances of going there would be very small. Okay. All right, so now we have understood how to go from here to here. There is a minimization condition on this. What we want to do now is something a little different and goes by the name of a Legendre transform. Again, Legendre transformations are very useful in a lot of manipulations that you might want to do, both computationally and in terms of analytic results. So computationally, Legendre transforms are used to define different types of ensembles in which the number of particles can change, the volume of your system can change, depending upon controlling different parts of the system. So let's understand what this means. First of all, notice that although we started our discussion with saying take a system, fix the U, fix the V, and fix the N, and then calculate the fundamental relation S of U, V, and N. It's somewhat hard to do this in practice. It's hard to isolate a system completely so that it exchanges no energy at all with the environment. Experimentally, it's not a natural thing to do because then you cannot probe the system. The moment you try and put a thermometer in or measure a property, you're interacting with the system and then it's no longer a completely closed system. So there's a practical aspect to making any measurement on a system that is truly and completely closed. So what one does, or what is a more natural experiment, is to take your subsystem here and put it inside some bath. So take the system S, consider a bath B, and the bath is assumed to be large enough that all the degrees of the freedom of the bath are at the same temperature T. Okay? Now remember that we said the equilibrium between two systems is obtained when they are at the same temperature. So the subsystem, once the subsystem is allowed to exchange energy with the bath, the subsystem also receives the same temperature T as the bath. Even if I start off at some temperature T of the subsystem which is not the T of the bath, the system settles down to equilibrium and finally it forgets about the state which it started out with, and in the final equilibrium state the temperature here is the temperature here. Note that a system like this is not perfectly enclosed, it can still exchange energy. So maybe in 1 second it gives a little more energy here, maybe the bath gives it a little more energy the next time. So even though it's allowed to exchange small amounts of energy back and forth, on average its energy is fixed and its temperature is fixed because it's in equilibrium. So this is a more natural way of doing an experiment because it doesn't prohibit your subsystem from interacting with the environment. It says it interacts with the environment in such a way that it is in thermal equilibrium with the environment. it's at the same temperature as the environment. So now you can say that, look, all of these functions here rely on fixing the energy or fixing the entropy. What can I think up a description of the system in which the variable that I tune is the temperature and not the energy? Okay. So let's just try and understand that a little more. We know that the definition of the temperature T is delta U by delta S at fixed V and N. By defining my subsystem to be in equilibrium with all of the stuff that is surrounding it, this whole bath, I'm saying it is at the same temperature as this. So the temperature is a variable that I have to continue. I can tweak a little dial here and change the temperature, wait a bit, and then the system comes into equilibrium with the new temperature. And then I can say what has changed. What was the average energy before? What is the average energy after? Does that have an interpretation in terms of the specific heat of the system, where I add a little bit of heat and ask what is the resulting change in the temperature of that system? Can I ask what is the specific heat, what is the heat capacity, or other quantities? Because now I can ask these questions as a function of temperature, which I can control very precisely because it's just a property of the bath. The bath is a system that is large enough that taking any finite amount of energy to and from it doesn't change the temperature. So if the oceans in the world are pretty much at the same temperature locally, if you want, so whether I put even if I put a tiny little heater inside the ocean, that doesn't change the temperature of the ocean that much, because the ocean is just so much more bigger and has so many more degrees of freedom, then that doesn't affect it, that are unaffected by the existence of one small little heater at one particular point. So now what we want to do is try and arrive at a description of the system that instead of having U here or S here, it changes the variable to the temperature. Okay? So what that is saying is, if I have, so let me just describe what this means in terms of this. Suppose I have some function y, which is a function of x. Here is x, here is y of x, and it's a function that looks like this. Okay? This variable here might be the energy, this variable here might be the entropy. This quantity here is like the slope of this curve here. So given one way of specifying the functions to say that given a point x, there is an appropriate point y of x corresponding to that, and there is a slope at that point that corresponds to this particular function here. So then you might have said, okay, I know t as a function of u, so t is delta u by delta s, where u is a function of s, v, and n. I'm going to keep these fixed, so I'm not going to worry about these. It's only the dependence upon s that I want. If I give you a relationship like this is some complicated function f of s. In principle, I could invert this so that for every s, I have an appropriate t, which means I can go back and put it into my expression for s, for u as a function of s, x, and t, and put t inside here wherever s appears, because I know the relationship between t and s. Now the question is, does that have all of the information as this initial curve here? So that is to say, if I know the slope here, let the slope be m, which is dy x by dx. If I tell you what the slope is, can I reconstruct the full figure y of x? The answer is no, and why that isn't true can be understood very simply by just looking at the following curve. Suppose I plotted y of x just as I did in that plot, but I plotted it in this manner. Here is one function, here is one function, here is another function, here is another function. All I have done is shift this curve upward by a common amount, some amount. Now notice that if I choose a point here, the slope here, and the slope here, and the slope here, and the slope here, all of them are the same. Okay? So just telling you the slope will not uniquely fix this particular curve for you. That is the point. There's a little more information that you actually need in order to fix that value. So let us examine what that should be. So suppose I have u here and s here, and it's sort of I have a curve that goes like this. I have a point here, here is the slope, and I want to ask what information do I need in order to specify this curve completely. The information that I will need is first of all the slope at any point, but also if I tell you what is the intercept, then I can describe this curve completely. So every point here is either for an x a given y or a slope and an intercept. I need two parameters to tell you. First, where is that point? What is the y corresponding to that point? And in the other case, what is the slope and what is the intercept corresponding to that slope? If I tell you the slope and intercept, I have given you all the information that you can take from x, y of x to m and some new function f of m. Okay, so that's going to be our logic. Now we want to try and see what to make of it in this particular example.
How did you make the analogy between the slope and that function?
How do we make?
Like, we want some f inverse of t is equal to s something something or s and some variable so that we can move inside.
Correct.
U as a function of t.
Correct. So one thing to do would be just to invert the relationship between t and s, so that given an s, I know what the t is. If I put that back in here, you might have thought this is all I need to know. But the point of plotting it like this is to say that's not all that you need to know. It's not enough to know the slope, because all of these curves have the same slope at the same point. Because any curve that is shifted up uniformly with respect to the previous one has the same slope at that point. So it doesn't fix the curve uniquely. Whereas the fundamental relation, that is this, is a unique way of saying fix this, then I know what this is uniquely. So the question is, how do we make sure that there is the same information in some new function, which is a function of t, as there was in the original function as a function of s. Okay? So let's just describe how to do that. So we're going to do this plot again. Here is our point, and here I have u, let us say, as a function of s. I have the slope here, and the slope is du by ds equal to t. Now the slope at that point is the same as this height divided by this part of the curve. But this part, suppose I call this intercept, let me call it f. This I will call u. So u minus f is the top part, is this part of the curve. This divided by s minus 0 is t. Correct? I'm just saying the slope at that point is just this height divided by that. So from here I get f equal to u minus t times s. So this is the function f, which in principle f as a function of t, u now where I substitute t for s has all of the information that I need. So I have to make the substitution at 3 points. U contains s, so I have to substitute for s in terms of t. S contains, over here I have to substitute in terms of t. And finally I get a function f, which is only a function of t. And now you notice that this particular way of writing this function f, given a particular t, has all of the information as in that original curve. Okay? So f goes by the name of a Helmholtz free energy. And it's just one of a number of free energies that one can define. the Helmholtz free energy is this new function f of t that is defined as u minus Ts, where all factors of s on the right hand side have been replaced by t using du by t ds equal to t. So, using this relationship I can now invert t to find t as a function of s or s as a function of t.
So this is true only for small u's and s's and t, right?
No, this is true in general. It really relies on the fact that there has to be that the relationship between u and s has a particular structure.
But we are neglecting that structure when we write u minus f by s, right?
We're not neglecting the structure. That is just a definition of the slope at a point. We're saying if the slope at a point is given by this expression, then this must hold. It relies on mathematical properties of u of s and s as a function of u that are not really of interest because they will hold in most cases that we will be worried about. The use of the Helmholtz free energy is that the Helmholtz free energy behaves similarly as a function of all of these other parameters x1 to xr, let us say, just like u did. That is to say, we minimize u at fixed s. Here at fixed t, we minimize f with respect to these. So, it is the same type of condition holds both for f and u. I have not explained that, but this you can take for granted for the time being. So, the same minimization condition as on u at fixed s on x1 to xr, on any of these other parameters that enter the definition of the free energy. Let us now do an example that will make things a little clear. So, let us write this example out. Let y equal to a e to the power b times x. So, this is y as a function of x. We now want to write the Legendre transform in which we take x and replace it by the slope p, which is dy by dx. Okay?
F is a u, right?
F is u minus Ts.
How did you come to t is equal to 2?
This one? This is by definition.
No.
Yeah.
T is equal to
F is the value here of the intercept. So, this point minus this point is the height. That is the value here of u minus f. That is this height here.
How did you come to this conclusion t is equal to t times t as a function of s and s as a function of t is equal to s? The one that next to the graph.
This one here.
Yeah.
This just says that I can invert the relationship between s and t or t and s, depending upon which I want. What I wanted to do was I wanted to write, since du by ds is a function of s and various other things, this is defined to be t. So, t is actually a function of s. That is really what I wanted to say here. If t is a function of s, I can invert this to write s as a function of t. Okay? Wherever I see s on this side, for example, I will see s here, I will see s here. I can substitute for t because I know what s is as a function of t. Once I do this example, it will become a little clearer what we are about. So, we want to transform the function in terms of x to its derivative dy by dx, which is p. So, dy by dx is a e to the power bx times b, which is p, correct? Because dy by dx is a e to the power bx times this this object itself and pulls down the factor of B. This implies that P over BA is e to the power Bx, and 1 over B log of P over BA equal to x. So take the log of, so P divided by BA is this object on the right hand side. Take the log on both sides. Log of P by BA is just B times x, because log of the exponential pulls down the argument for me. So log of P divided by BA divided by the B on the right hand side is x itself. So now this is the relationship between x and P. So now the Legendre transform is some function of P, let me call it psi of P, which is y minus P times x. But now I must substitute for x wherever I see it. Okay. Now y is a e to the power bx. So this is a e to the power b, and then I must substitute for x. Okay. So let's do that. This is 1 over b times the log of p divided by ba, correct? So that is substituting for x. This is y of x, which I must now substitute for p. If I must do that, everywhere x comes, I must substitute this expression here. So when I put y as a e to the power bx, this is a e to the power b times x, which is 1 over b log p by ba. Again, there is one more term on the right hand side, which is minus p times x itself, which is p divided by b, that's a term here, times the log of p divided by b times a. Exactly. So just as we did it here, this is when I wrote f equal to u minus ts, u is my original function, this is the slope, and s is the variable that enters the original function. So u is a function now of y, the original function, the slope is p, and the original variable s is x. Okay? So now we can take this and simplify it. First of all, the b and the b go away. I can write the a outside. Exponential of log of p by ba, e to the power log anything, is that thing itself, because exponential and the log are like going back and forth between each other. So the exponential of log of p by ba is just p divided by b times a. Do you agree with that? And the second term here is minus p divided by b times the log of p divided by b times a. There's nothing I can change there. So the only simplification I can make now is to delete these factors of a that are common between the numerator and the denominator. I get p divided by b minus p by b log of p divided by b times a. This is now my function psi of p, which is the Legendre transform of my original function. So this just illustrates what I need to do in order to take a Legendre transform. Now, while this is just a simple mathematical example, over here it means something very specific and physical. It says I want to change the variable that I can control from S. Rather than fixing the entropy of the system to be S and then trying to measure things about it, I want to fix the temperature of the system to be T. In order to do that, what I imagine is I take the system, I put it in a huge bath. So whatever energy, small amounts of energy the system gives a bath doesn't change the temperature of the bath. So the bath, as far as the system is concerned, is something at fixed temperature. Once my subsystem is in equilibrium with that bath, it can exchange energy back and forth. So its energy is not fixed, but its temperature is fixed, which is the derivative of the energy with respect to the entropy. To describe such a system, I use not the original relationship U as a function of S, V and N, but now a new relationship between a free energy called the Helmholtz free energy, which is a function now of the temperature, the volume and the number of particles. The advantage with using F is that F is a quantity that is also minimized in equilibrium, just like the energy was. Okay? That's going to be the logic which we will pursue.
So is this Helmholtz free energy same as Gibbs free energy?
No, the Gibbs free energy corresponds. So remember that, maybe I should just rub out some part of this. The Helmholtz free energy starts off by taking U as a function of S, V and N and writing from here F, which is U minus Ts. And now F is a function of T, V and N. This is a Helmholtz free. That's exactly what we did so far. But now similarly, I can say that, look, I'm not going to worry about constraining the volume of my system. I'm going to let the volume fluctuate. But the way I'm going to do that is to allow it to be in contact with some bath with fixed pressure. Just as I started off with a bath with fixed temperature, now my bath I can also allow it to have fixed pressure. So that means that the volume of the system is not precisely fixed but can fluctuate, subject to the condition that what is the pressure inside must equal the pressure outside. Again, this is a natural thing to do for some types of experiments. For example, most chemical experiments that you do are done at atmospheric pressure. You don't control the volume of the system, that can fluctuate, you're working with an open test tube. But now that pressure inside your system must equal the pressure outside in equilibrium. So in order to do that, you can make one more transformation of this. You can say, I'm going to eliminate the V in terms of the pressure. So if I write G, which is F plus PV, which is U minus Ts plus PV, then G is a function of the temperature and the pressure and the number of particles. And this is called a Gibbs free energy. It's just one more step of Legendre transform. And again, once I fix T and P, so this describes a system that can be in thermal equilibrium with its surroundings and also in pressure equilibrium with its surroundings. It has the same temperature as inside as outside and the same pressure inside as outside. And that is described in terms of a Gibbs free energy. So all of these things you might have learnt about separately, all of the different ways of defining free energies, but they all follow simply as Legendre transforms step by step from a basic quantity which we started out with, which is U. Now similarly, we can also go back from a F to a U by doing an inverse Legendre transformation. Okay? So all of these quantities, the U, the F, the G and anything more exotic that you might think of, all of these really describe the same function, same functional behavior, because by construction we said F contains all the information that U does. What is the pair x comma f of x is now replaced by the slope m and psi of m. Okay? So we might come to describe the Gibbs free energy a little later when we talk about chemical reactions and why in equilibrium reaction constants are related to free energies and so on. We will describe that a little later from the point of view of statistical mechanics. But it is good to have these definitions in place well before we do that. So now let's think a little bit about a really important question, which is, what is entropy? So the whole question of what is entropy comes back into saying, what do we think about this new thermodynamic coordinate or variable that we have, it surely must have some fundamental definition or description in terms of all of the microscopic constituents of the system. Remember how we start off philosophically. We said that, look, thermodynamics is only concerned with large measurable aspects of the system. The volume of the system is certainly large and measurable. The number of particles is large and measurable. You know the density, you can take a weight of it. But what about the molecular state of all of these internal constituents? We know that it's made up of atoms, but what variable describes what is the state at which all those atoms are in? So that's the question not for thermodynamics but for statistical mechanics. But the entropy is in a sense our single number that describes the state of all of these internal coordinates or the internal positions of all of these positions and behavior of all of these microscopic constituents. So we must look at that to try and understand how can we think of entropy. And the main sort of pioneering work in understanding what is entropy was done by Boltzmann. So the Boltzmann wrote down a formula for the entropy in terms of all of the microscopic degrees of freedom. So he said the entropy S can be defined as the following quantity. It's a Boltzmann constant Kb. Remember that we saw this is 1.38 into 10 to the power minus 23 joule per Kelvin. But then what multiplies it is the log of a quantity called omega as a function of u, v and n. So this is Boltzmann's great insight for the definition of the entropy. I haven't told you what this is, but this is an equation that is Boltzmann's tomb in Vienna contains this equation on the top of it. Means that it was extremely important contribution. This is the number of states available to the system So let me say number of microscopic states available to the system at fixed u, v and n. So what Boltzmann is saying is that look, there are many states that are available to the system. Once I tell you how much energy I have, what is the number of particles, etc., I can sort of imagine mentally that each of these is some state of the system, and each of them that I mark with a little circle is some allowed state of the system. That is to say, the system could be in this state or any sort of neighboring state around it. I count the number of states that are accessible to the system. I take the log of that, that is the entropy. So this definition is very important and is very fundamental to the science of the study of statistical mechanics. So given that I have fixed the energy of the system, I find out all of the microscopic states of the system that have that energy. I take the log of that microscopic number, multiply by Kb, I wind up with the entropy S. There are some sort of technical issues associated with this definition. Suppose u can vary continuously. Then it's not usually, we've done this argument, we should not say precisely what that u is. We say u can be in some small shell of energies between u minus du and u plus du. That's the limit to which I can describe that. The same thing that we did when we went from probabilities to probability distributions. We say it doesn't make sense to say it has precisely this value, but it does make mathematical sense to say it can be somewhere in this very small range given by u, in this particular case, u and u plus du. So these are the sort of distinctions that we have to be a little worried about if we wanted to be very much more specific about the definition. Okay, there are various other assumptions that go into this. So this is just counting the number of states that are available to the system with fixed energy. But in addition, you need a little more justification than that. You need to say that the system explores or can be in any one of these states. No state is forbidden to it for any reason. If it's allowed, and the system can be in it. That goes by a specific technical name, it's called ergodicity, but we don't need to worry about that, we just need to sort of describe it. Yeah. Ergodicity reflects the fact that the system can be in any one of the states that is allowed to it, and visits all of these states. There's nothing that is forbidden, provided I specify u, v, and n, any state consistent with the specification is a possible state that the system can be in.
Provided you specify all possible unions.
Yeah, so given, not all possible, once I fix u, v, and n, that isolates a certain number of states. For example, it isolates these states. All of these states are consistent with the fixed u, v, and n. Maybe this state is consistent with a different value of u in the same v and n. Maybe this state might be consistent with yet another value of u with v and n. But given the specification of this, there's only a certain number of states that are consistent with that. Now the system can, in principle, the argument is the system can be in any one of these states with equal probability. It explores all of these states together.
So you're saying that, or it happens, or?
So that is, it's an assumption that has to be proved for specific models. In practice, for systems in equilibrium, that turns out to be true. For systems which are not in equilibrium, it turns out not to be true in general.
And the system does take all these things.
That the system explores all of these states.
Only for systems that are in equilibrium.
For systems that are in equilibrium, the fundamental hypothesis that goes into writing an equation that relates the entropy to the number of states is that all of these states are equally possible and visited by the system.
So here one point shows that it's a unique value of u, v, n, right?
So I'm saying, given u, v, and n, all of these are equally possible. It's not a unique value. This is not, the u, v, and n is the same as u, v, and n here, is the same as u, v, and n here. So given u, v, and a state is some microscopic specification of all the states of the particles. Suppose there are n particles. So I might say, let all those particles, let n minus one of those particles be at rest, and the nth particle move with the full energy of the system, full kinetic energy of the system. So that is one state of the system. Or I could say, let the first particle move with the full energy of the system, but all the other n minus 1 particles be completely stationary at fixed positions. These are two different states, because I specify a state by saying what are the positions of all the particles, what are the momenta of all the particles. Okay. So these are different ways of assigning the same amount of energy to the different particles inside the system. So these could be two different points inside here. But all of these points in this pictorial way of drawing it correspond to the same u, v, and n. So the statement that justifies this, that says you can write this, provided all of these states are equally probable. Okay.
Does this relate to degrees of freedom? Even specifying certain constraints.
So the degrees of freedom specify all the different values that these states can take. For example, the degrees of freedom appropriate for a bunch of particles are all the positions of the particles and all the momenta of the particles. Because from physics, from basic physics, physical mechanics, I know that if I specify all the positions of momenta, I've specified the system completely for you. So those are the fundamental degrees of freedom, but they can be different. You can have degrees of freedom that look like spins. You can have degrees of freedom that are even more complicated than that. All of these are allowed. Okay. Now we are going to use this in a very particular and special way to obtain one important result in statistical mechanics. The way we are going to formulate it is to say, I'm going to look at a large system which is closed, the larger system is closed, but it's made up of a subsystem and a bath. The subsystem is in equilibrium with the bath in terms of being able to exchange energy with it. The subsystem can exist in a bunch of different states. The energy of one of these states is E sub j. What I want to ask is, what is the probability of finding the subsystem in a particular state with energy E sub j? Okay. So let me write that out in words. This is the probability of finding the subsystem. I can call it the subsystem or the system in a particular state with energy E sub j. That's a question that I want to ask. So that might be the same as asking, what is the probability of finding the system here at this point, or at this point, or at this point? This is just a specific state of the system. All of these states of the system are consistent with the fact that they are same u, v, and n. So what I want to ask is, what is the probability of finding a system here, or here, or here, or here, or here, or here? Provided I construct the system in the particular way. I allow it to be in equilibrium with a bath at temperature T. As I said, this is the most natural way of thinking about a system, in which you don't control its energy precisely, but you control the temperature of the bath with which it's in contact. So let's start by writing the probability of finding the system in some energy state J is just the number of states of the bath with energy E total minus Ej divided by the number of states of the bath, so we say omega total of E total.
So the energy of the bath is different from EJ?
The energy, the total energy is E total. So let us say E total is, so that is the bath plus this, plus the system. So E total can be divided into some part that belongs to the bath, which is Ej, and some part that belongs to the, some part that belongs to the system, which is Ej, and some part that belongs to the bath, which is E total minus Ej. Okay? So what this is saying is fairly straightforward. This is saying that the probability of finding the system in one particular state, the fixed energy, is the same as the number of states of the bath with the remaining amount of energy. Once I fix this, I have told you everything about this. I've exactly fixed this. Now I have E total minus Ej to be distributed among the bath. The more the number of states of the bath is, the more the probability that this will be found in that state. So that's why this factor enters here. But it must be normalized because it's a probability, and the normalizing factor is always the total number of states of everything, bath plus subsystem. So stare at this a little bit if you're not completely sure about it, and then we will go on to use this to derive a certain result.
This is the same as writing number of states of the system as a function of EJ, right?
That's right. So this, but this is the probability on the left hand side. So the probability is,
You write omega system E of J, so that's the same as the upper numerator, right?
that, so this is the number of states of the bath. I'm now going back to this omega here, where it's the number of microscopic states available to the system.
Okay. I have
Okay.
a question. The number of states of the system, is the number of states additive, like the entire bath plus system, such that the number
No,
of
the
states
total
of
number of
bath-
states is multiplicative. For any one state of the system, I can have a large number of states of the bath. So the total number of systems, number of states of the system is number of states, total number of states of the whole thing is number of states of the system into the number of states of the bath. But only a fraction of that are allowed given a fixed energy, because the total energy of the subsystem plus the bath must be a constant, which is why we have a constraint on the total energy. So this is like saying, let us divide the energy between the subsystem and the bath in all sorts of different ways, and just calculate the total number of ways of dividing this. Okay. This is one particular way of dividing it. I have fixed a state of the subsystem and giving all the rest of the energy to the bath, and the bath can be in any one of those states. This is summing over all possible states as well that this can take. Okay. All right. So now remember that S equal to Kb times log of omega. So I can take this here and write this as e to the power S divided by Kb, where S is a function of E total minus Ej, and I must do the same thing at the bottom. So write this as e to the power 1 over kb S total of E total. Let's now simplify this in the following way. Let us say here is my subsystem, here is my bath. On average, the subsystem has energy U. On average, the bath has energy E total minus U. So U is the average energy of the subsystem. I'm going to use that to do one simple thing here, which is I'm going to write S over kb of E total minus Ej. I'm going to write this as S over kb of E total plus U minus Ej. All I did is add and subtract factor of U.
Where did we get the C2 power? It's kb.
We got this from this term here. This term here. I didn't write the E factor, I only look now at this particular factor. S over kb, E total minus Ej. I did something that is a no-brainer, which is I added and subtracted the same number, which is U. Okay. Now I can do the following, which is I will write this as S over kb. Let me just put a factor of 1 over kb here outside. Write this as S of E total minus U. And then over here I have U minus Ej, which is this term here, delta S by delta U, and so on, higher order terms. What I am doing is, I am saying, this is a large, this minus U, let me put a minus here and a plus here. This is the average energy of the bath. I am going to say that this quantity is small, and I am going to expand about this. So this is, first of all, if it's small, I assume it to be 0. Then that's the first term here. This is the next term in that expansion. So what I'm doing is, it's just saying if I have a function f of x plus some quantity a. This is just f of x plus a times f prime of x plus a square times blah 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 blah. So this is called a Taylor series expansion, which you've seen before. I'm just using the same idea in expanding s as a function of this. So this part is for me my x, this is for my a. Okay? So this is s, first of all the 1 over kb comes outside, s as a function, so the first order term is f of x, which is s of E total minus U, this part. This is the little extra part which is a. So it's a times, which is U minus Ej times the derivative of s with respect to U, which is f prime of x. This is df by dx. Okay? But this quantity we know what it is. This is 1 divided by t. So now that particular result simplifies to say that 1 over kb s of E total minus Ej is 1 over kb times s of E total minus U plus U minus Ej divided by the temperature T. And provide this is small, I can neglect it, these higher order terms that appear here. Okay? Simple mathematics, nothing more complicated. I now want to do the same thing here. So I'm going to write 1 over Kb times S total of E total. This is the same as 1 over Kb times S of did I define that correctly? I should put in S of bath there. And here I should put S of bath, right? And here this should be S of bath as a function of E total minus U plus S of the system at energy U. This should also be S of the bath to be completely consistent with what I have been writing here. I should also write an S of the bath here, an S of bath here, and then I don't need this is a derivative of S of bath with respect to U. Okay? Is everyone clear about that? Now notice that when I take the exponential, I have one factor in the numerator, which is 1 over Kb S bath E total minus U, and I have one factor in the denominator, which is 1 over Kb S bath E total minus U. I must go back and put them here, put both those factors back into this. Okay? So let me just do that. So you can write P of Ej equal to e to the power 1 over Kb times S of bath of E total minus U plus U minus Ej divided by T. I am going to ignore higher order terms. I am going to divide this by e to the power 1 over Kb times S of bath at E total minus U plus S of U, where this S refers to the subsystem. Now I can cancel this factor with this factor. Having done that, this now simplifies P of Ej, probability of finding the subsystem in state with energy Ej, is exponential of 1 over Kbt times U minus Ej. This is what sits on top, divided by e to the power 1 over Kb. And now I am going to multiply and divide by T. So I get 1 over Kbt times T times S of U. You agree that I can do this because it's just deleting T from top and bottom. This is the same as this term here. Okay? So then this further simplifies to e to the power 1 over Kbt times U minus T S into e to the power 1 over Kbt with a minus sign times Ej. So let me just write it a little neater. This is minus Ej divided by Kbt. You will recognize this quantity here as U minus Ts to be what we defined earlier to be the free energy F. Remember, this is how we took the Legendre transform with respect to the temperature of U. Okay? So this becomes, I will also make one more definition which is to define beta to be 1 over kb times t. So then with that, I can write this as e to the power beta times f into e to the power minus beta times ej. Do you agree? I can just write that term out again a little more neatly. So then, probability of the finding the system in a state with energy Ej is e to the power beta times f into e to the power minus beta times Ej, where beta is 1 over kBt. Are we clear with that? We just have a few more steps to go. The next step is to define a quantity 1 over z to be e to the power beta times f. Therefore, z equal to e to the power minus beta times f, or f equal to minus kBt times the log of z. This is just a definition of one thing in terms of another thing. So the probability of finding the system in a state with energy Ej then becomes 1 over z e to the power minus beta times Ej. We can also define z by the requirement that if I sum over all states j of the subsystem P of Ej, this quantity must equal 1.
Z as in a complex number.
No, z is defined as, it's not a complex, it's just a quantity that I will define to be z. Okay. So this implies that if I take the sum over all j, e to the power minus beta Ej, this quantity now must be z, because only then can I get z in the top and the bottom to cancel, and this sum to be 1. So this is the sum of all my definitions. Here is one definition of z in terms of the states of the system. Here is the definition of the probability of finding the system in a particular state in terms of z and Ej. And here is the definition of the free energy of the system in terms of z. So this could be equation number 1 of importance to us. This was equation number 2 of importance to us. And this is equation number 3 of importance to us.
So here states are discrete. Discrete.
So for the ease and simplicity of describing it, I chose these states to be discrete. So I could write just simple sums here. But everything translates into the case where they're continuous. It's just that instead of a sum, I have to write a little more complicated notation involving the density of states at energy E, or some way of counting all of the states. Z has a specific name. Z is called a partition function. F, we already wrote down the name. This is a Helmholtz free energy. And this fundamental relationship here defines the probability of finding the system in a particular state. And this, this is called, I think, the Boltzmann-Gibbs form. of the probability of finding the system in a particular state, J. Okay? So these are among the most basic results in statistical physics. Boltzmann and Gibbs together were people who devised this particular way of finding the energy of the system using the result that Boltzmann had derived for the entropy. So this, you can say the probability follows the Boltzmann-Gibbs form. I don't think it has a different name apart from that. But as I said, these are very important results because they are saying that suppose I have a system. All I know about it is that it has some set of energy states. I can make measurements on that system. Sometimes I might measure it to be in this state, sometimes I might measure it to be in this state, sometimes I measure it in this state. But if I ask, take a large number of measurements, what is the probability that a good fraction of those measurements I'm in this state? That fraction, that number divided by the total number of my measurements is the probability of finding it in that state if I make a large enough number of measurements. What we have claimed here is that we can now calculate that number, calculate that probability. And remember that if I can give you the probability of finding the system in any one of its states, I can calculate any probability of interest to you in equilibrium. I can say if in this state it has energy E, in this state it has energy E prime, and I know the probability of finding it here and the probability of finding it here, I can find the average energy, I can find the fluctuations in that energy, and all of these terms I can write down.
Can you explain what does the second equation mean physically?
This one here, this is just a definition. We define Z, we define first of all F in terms of Z, and this is just saying that we can now calculate Z in terms of these states. So this is
2r minus beta j represents the
all, this is Ej is, so this is all possible states of the system. So this is the sum over all possible states. I can have a large number of states. Some of those states can even have the same energy, I don't care. But this is the sum over all those possible states with this factor inside. This sum is a partition function. As it turns out, this is the most basic quantity in statistical mechanics because these probabilities, all of these other quantities, we can derive many different things from the partition function. One simple thing that we can derive is the free energy itself by taking minus kBt times log of Z.
what does this Helmholtz free energy, what does it physically mean to us? Like when kBt ln
So the Helmholtz free energy is useful for many things. One thing is that you know that in equilibrium, if a system is in equilibrium at a bath with temperature T, then its Helmholtz free energy is minimized. So it's a way of saying what is the state, the thermodynamic state of that system. You say it has a large number of states, but if it's in equilibrium with a bath, choose a state that has the minimum value of the Helmholtz free energy. So it's as useful as the entropy. For example, when we said the entropy, our calculations about the entropy were a way of understanding what is the state that the system chooses. It's a state with the maximum entropy. Similarly, but that is for a system that is completely isolated and has a fixed energy. Similarly here, this is a system that is not isolated. It can exchange energy with its environment, but it's at the same temperature as the environment. Then the question is what determines that state? And the answer to that question is calculate the free energy and find the minimum free energy at that temperature. Look only at the states that have a fixed temperature. Find the minimum Helmholtz free energy among those states. That is the state that the system will pick out.
So we can do the transformation to get this kind of thing to other extensive variables.
You can. For example, as I said, we went from the Helmholtz free energy to the Gibbs free energy. Then the answer would be, if for a system that is in equilibrium at a fixed temperature and a pressure with some bath that surrounds it, the quantity to be minimized is the Gibbs free energy of the system.
For this, the only temperature was the same with the bath, but for
That's right.
the pressure and
The pressure and the temperature are both the same as that of the bath. And that's a natural way of thinking about chemical reactions, where the chemical components don't change, but the reactions are typically done in some open beaker where you have the same pressure as atmospheric pressure, and it's a temperature because you're keeping the temperature constant. Yeah, it depends. Remember that we started off by saying you have an energy U as a function of S, V and N. We eliminated S in terms of the temperature. We can eliminate V in terms of the minus pressure. We can eliminate mu in terms of the chemical potential. All three we can eliminate. So the simple choice corresponds to eliminating T, which gives you the Helmholtz free energy, and eliminating P, which gives you the Gibbs free energy. But you could do also T and mu and keep this as a function of V. Depending upon what is the situation that you want to model. If you want to model a system of fixed volume which can exchange particles, then you might prefer to keep the V here, but keep mu and T on these two sides.
Sum of all the possible states is related to omega, right?
Omega is a total number of states that we started out with, but this is just the states of the system. Remember, we have a system here and we have a bath here. The system has a number of states here. This is only a property of the system.
And even then it would be e raised to beta Ej, right?
Ej, where J is all possible states of the system. The bath only comes in fixing the value of beta because it fixes the value of T. Otherwise, we forget about the bath.
Negative sign actually.
The negative sign has to come here because it's part of this definition, no? The way we derived it. What's the problem with the negative sign?
No, just when we defined sigma first, it was from that we can get that e raised to S by kT. Kb.
Yes.
The negative sign.
So then we expanded that, right? We wrote the factor on the top was e to the power S of the bath as a function of E total minus Ej. Then we wrote E total minus Ej to be E total minus U plus U minus Ej.
Yes.
Correct? Then we expanded this quantity.
We got the minus Ej part,
Hmm.
but I am asking that then can we say that it is the sum of the whole states actually?
Why? Why not? Because what we derived is this thing. We derived the probability of finding the system in one particular state, Ej. That's exactly what we did now. Now, if you want to say the one constraint on this, the system must be in some state. So, if I sum over these probabilities, I must get 1. That's all I used here. I summed over the probabilities to get 1. Use this definition to define Z. Okay, so this particular sum is defined to be a quantity called Z, called the partition function. And this is useful to us because for one, it helps us define the free energy. But this is where all the properties of the system enter, because you have to know all the states of the system and what their energies are. If you know all the states of the system and what their energies are, you can calculate this object and thereby calculate Z. So we might do some.
Is the number of states available for subsystem at energy Ej is equal to the number of states available for the bath with E total minus Ej?
That's what we said. We said fix the energy of the subsystem, fix the state of the subsystem, and then the bath has all of these other states which it can take, which have energy E total minus Ej. So give the rest of the energy, fix the state of the system to be one particular state with energy Ej, or the rest of the energy goes to the bath. The bath has many states. It can in principle have many states with energy E total minus Ej. Count those number of states. That gives you omega of the bath with energy E total minus Ej. So have a look at it and we can discuss this in more detail the next time. There are more questions.